next speaker is Felix Talk, and he also was one of the tutors at the workshop the last 3 days. And he just recently finished his master at the MIT Media Lab in the Tangible Media Group. And he will speak about his final thesis and his concept of radical elements, and talk about a historic example and tell stories how to explore the intersection of musical instruments and computer interfaces.
Yeah.
Welcome, Felix.
I'm Felix. I recently graduated from Hiroshi's group, the Tangible Media Group at the Media Lab, and was lucky enough to work with a lot of you guys today, actually for the last, I think, around 36 hours, to do some really, really cool pneumatic stuff. And today, I was just going to give you a little glimpse of the kind of applied stuff that I've been doing, and then totally abandon that and talk about the things that I was thinking about while I was doing that. Kind of the practical stuff of my thesis was this material called unimorph. And it is about a dynamic material that can be affected by the environment. Like here, the heat of the light bulb actually makes this flower open. Or actually by computational control. And so here are some form primitives that you can kind of design in, basically in CAD software, and then computationally control the extent of the actuation. And because we are thinking about how you can apply some of these technologies, I made this one example that is a bookmark that once it gets too dark, it kind of curls up and helps you read things again. But for me, making these kinds of technologies is not just about making cool examples, but also kind of enabling other people to do the same thing. And that's also why we did this workshop today, not on this, but on another technique. And this, what you just saw, I'll just show it again, actually, is basically the whole documentation. This is all you have to do to actually make something move. It's a very simple process. So this is all online. You can look it up. And so today, I'm going to talk about what I was kind of thinking about while I was doing all of this, and what I think should be explored a little bit more. So, really long time ago, this is Doug Engelbart. Doug Engelbart once actually invented basically the computer that you're all using right now. This is actually one of the, it's really old, you can see it by the high pixel resolution. He basically invented the computer that you're using that way. He had this thing called the mother of all demos. And I'm going to kind of see how what he did might be actually achieved in a bigger in a bigger context with more dynamic materials. So this was his vision. He thought we would use a mouse, but we would also use this other thing. And he called that a chord set. The problem was that was really hard to learn, because the chord set on the left is basically a one-handed keyboard, where you have 5 keys, because you have 5 fingers. And then you can kind of basically just press them in certain patterns, and you would, without ever moving your hand to the keyboard, actually just use your computer in a more efficient way. And then some of you might know that, well, this guy Steve Jobs came in and was like, this is awesome, but I have to make it super simple. I have to basically have people come to the store and kind of understand right away how this works. They don't have the time to actually learn something in the store. They shouldn't be frustrated there. They should just go in there and use it right away. So he took all of these beautiful but really, really hard to learn concepts and kind of boiled them down to the one-click mouse. And when Doug Engelbart saw this, he was he had a lot of other concepts, but one of the things was for him was basically he said for him this was the difference between riding a bicycle, which was his invention, and riding a tricycle, which is easy to learn, but really doesn't get you to a lot of places. And he actually said, in order to push the envelope of human effectiveness and intellect, you can't be just confined to a small vocabulary of grunts and clicks, which he called this. And he actually imagined, the language that he used already kind of hinted that he actually imagined interacting with a computer much more like we interact with instruments, like something that you can actually kind of master. And he called the left hand a chord set, right? Which is kind of like what is something that actually occurs in musical instruments. So I kind of looked into musical instruments and saw if there was kind of the opposite direction where people go into digital music and how they learned about this. And I found this one really interesting story that I just wanted to share here, which is the story of organ building in the 20th century. I didn't know that I was ever talk about that. That happened in the early 20th century, called the organ revolution. And it's a really interesting story because basically in the 1920s there was a lot of basically electrical systems were kind of becoming like flooding the market. There were like electromechanic valves and just electrical keys, and organs are really hard to build. So the organ makers were super happy. They were like, we'll just take all of our complex mechanical parts and just use wires and valves for everything. And they built these way more complex organs because they could then. But all the organ players were like, this is not what we like. This is actually not a really great experience for us to play this. And I'll show you later why that actually happened. And so for them, they, like after 40 years of kind of exploring this, they just abandoned electrical organs and went back to the classical mechanical design. And so perhaps to give you a little understanding of why they did it, here's like a little animation that I found online, how actually organs work right now still and used to work before the electrical organ. So there's basically, you see there's just a mechanical connection, a very complex one, and there are like little like force amplifiers in there that connect your little key to this big organ pipe. And that actually kind of creates not just a sound, but you also feel the way that you open the valve that is like very far away from you. And before you even hear the sound, because often organs are really far away, you actually feel the air going through the valve already. And that's actually kind of cool. There's like a haptic sensation that kind of comes with the material, with the instrument, and it's a kind of a bidirectional nature. And that's kind of true for every instrument, right? We don't just hear the sound, we feel the strings of a violin, and we kind of feel the body of a guitar vibrating. And so Richard Isaacs, one of the leading mechanical designers and organ builders of Fisk, which is one of the biggest ones, said this beautiful thing where he like basically said, we have returned to the first principles of organ building. And interestingly, I think actually the last part of this is the most important, which is the importance of the organist feeling the pressure of the organ back on him. So there's this bidirectionality. And actually, funnily enough, they call the 40 years in which they experimented with electrical system the dark age of organ building now. And so even though our devices are white, I claim that actually we are right now in the dark age of human-computer interaction, where we touch the computer, but the computer never touches us back. And so I have some thoughts that, and kind of like almost like a little toolkit and of things that I think we can explore more to kind of change that, to actually allow the computer to touch us back. So the concept that kind of actually Fisk already described is the concept of a transducer. A transducer is an actuator and a sensor, so something that kind of can convert physical quantities, so pressure, brightness, temperature, any kind of movement into an electrical signal, and the bold part is the most important part, vice versa. So it's kind of like a translator between the language that the computer speaks, usually electrical signals, and the language that we speak, which is physical things. And so usually when we interact with materials, you just like you basically act on the material. Let's say you like bend a piece of wood and the material acts back on you. And then basically if you do this like radical element transducer theory where you put something in there that can not just sense the input but also act on you, the material actually truly mediates between not just the material anymore, but the computation and you. And that's kind of where material really just, not just as a passive kind of material in between, or like, yeah, passive interface, but really like is able to mediate for you and kind of unlock some of the potentials that you have. And they're kind of hidden in plain sight all around us. And that's kind of the interesting part why I wanted to talk about this. So a speaker, for example, we usually use them as speakers. They're kind of output devices. But some of you might know if you like plug them into the microphone port, all of a sudden, you actually have a microphone. So a speaker as an electromechanical device actually goes both ways. And actually, if you look at most electromechanical devices, they kind of do that. A solenoid, when you actuate it, create an electrical signal. And not just but when you also put an electrical signal onto it, it kind of moves. DC motors, which are kind of the most pervasive little motors, when you spin them, you might know that from like your dynamo on a bike, actually generate power. And the same goes for stepper motors. And we can even assemble them where you have like a servo motor that has on the one side a DC motor, but also a sensor that kind of coupled together create this, well, transducer nature, or kind of bring it into a linear motion form. So you can make electromechanical parts that you kind of assemble, but you can also actually go into the materials side and find on a molecular level materials that can actually mediate between computers and humans. So a piezo, this crystal that you just saw, actually comes in this beautiful form factor that can be used as a kind of vibration speaker instance, but also actually as a sensor at the same time. And perhaps another one that I think is kind of interesting is a Peltier junction that converts electricity into temperature and the other way around. So it's not just movement and transformation, but actually it's the whole level of properties that materials can have. So I kind of dug into this and made this, I call it the periodic table of radical elements. And this is just like a kind of a start of exploration into this. So these are all materials, and the order is still kind of weird, but they basically can do this. That's a beautiful picture. They basically can transduce, can connect the both sides. And actually, like, some of them, these ones are the electromechanical ones, and then these ones are kind of the material-based ones. And I personally think that when the computer touches us back, we are more willing and more engaged into actually learning the hard ways that Doug Engelbart kind of imagined us using the computers, and kind of switch from the tricycle to the bicycle. And so his daughter, Christina Engelbart, said, if we were willing to practice and learn these more complex ways of using computers, we could interface with them in more efficient and expressive ways. So that's it.